Warning: alkyl halides are carcinogenic. Magnesium is a reactive flammable metal. Diethyl ether is volatile and highly flammable. Wear gloves and work outside in a fume hood. Fire safety protocols must be in place. Greetings, fellow nerds! Carbon is the backbone of organic chemistry, and finding ways to connect carbon to carbon is a critically important operation that organic chemists are always trying to find new ways and tools for. One of the most famous and oldest reactions to do this that is still used extensively today is the Grignard reaction. In the most basic application, an alkyl magnesium halide, also known as a Grignard reagent, reacts with a carbonyl compound to produce a longer chain alcohol. But this isn't the only application. Amines, peroxides, and carbonyls can also be made, and coupling reactions as well as rearrangements may also be performed. For this video though, I'm just going to focus on doing very simple reactions of making tertiary alcohols. I want tertiary alcohols to perform some amateur research in making alkali metals like potassium. I'm going to start by making some small tertiary alcohols like 2-methyl-2-octanol and T-amyl alcohol, and then by changing the reagents, I'll try and make 3-ethyl-3-pentanol. Finally, I'll attempt 7-hexyl-7-tridecanol. We're also going to learn and use a few chemistry tricks like sodium drying, steam distillation, and Dean Stark drying. Now, of critical importance is to have high purity solvent. Grignard reactions are very sensitive to water and air as well as reactive impurities like alcohols, acids, and so on. So the solvent must be rigorously purified to ensure reliability and yield. Now, I've already made a complete video on purifying highly contaminated diethyl ether up to Grignard quality, so I won't go into it here. But briefly, the diethyl ether was reacted with potassium hydroxide and sodium metal and then distilled to remove the impurities. This is the first step to doing Grignard reactions. Now the next step is to make the Grignard reagent. We start with 12 grams of high quality magnesium turnings. Mine is fresh out of a new container, but you may want to grind yours a bit in a blender to expose a fresh surface if you have an older or lower grade source. Now we add in 200 milliliters of our previously purified diethyl ether. High quality solvent is very important for the reliability of this reaction. Ethereal solvents like diethyl ether or tetrahydrofuran are the preferred solvents for Grignards since they solvate the organometallic alkyl magnesium halide produced. On top of the flask, we attach a Claisen adapter so we can affix a reflux condenser and a pressure equalized dripping funnel containing 100 milliliters of diethyl ether and 60 grams of bromohexane. This is the same bromohexane we made in a previous video. Now we need to activate our magnesium, basically etching off the surface so it becomes reactive. There are a number of ways to do this, so I'm going to try a few until one works. First, I'm going to lift the dripping funnel and directly inject 2 grams of pure bromohexane into solution and let it sit for 10 minutes. If it works, we should see some bubbling or clouding as the reaction starts by itself. Looks like nothing is happening yet. I'm going to start stirring it now for about 10 minutes and hopefully the reaction will start. Okay, still no obvious signs. Now I'm going to drip in about 5 milliliters of the bromohexane and ether mixture from the dripping funnel and wait another 20 minutes. The reason why I'm waiting so long between each of my steps is because there is usually an induction period before the reaction starts. If you go too fast, you can enter thermal runaway as you pile on all the activation steps. Ether boils incredibly easily and you can lose the reaction that way. One of the main reasons why this video took so long was because of blunders like that. I simply went too fast and added too much bromohexane without giving it time to start up. Anyway, looks like it's working. We're seeing clouding of the reaction mixture and it's also bubbling very slightly. I'm going to keep running it a bit longer and hopefully all the magnesium activates. Usually when it's ready, it'll start to clear up again. And it looks like it's happening about now. We now have activated magnesium as well as a small amount of Grignard reagent product. At this point we can start slowly adding the rest of our bromohexane mixture. Since the magnesium is activated, it'll react vigorously without an induction period, so drip it in slowly and adding in at a rate that it just starts to reflux. Make sure your condenser has rigorous cooling to keep your ether from boiling off. Cooling with ice water is recommended. Dial back the rate of addition if it goes too fast. It's very easy to go into thermal runaway on a preparatory scale like this if you're impatient. So what's happening is the magnesium is reacting with the bromohexane to form hexyl magnesium bromide. This is our Grignard reagent. It is truly an organometallic compound where we have a carbon bonded directly to a metal. Now students occasionally make the mistake of labeling this as the Grignard reaction. This is not the Grignard reaction. This is just the formation of the Grignard reagent. The actual named Grignard reaction is the next step where this stuff is reacted with a carbonyl compound. The confusion arises because in most Grignard reaction procedures, making the Grignard reagent is a part of it. So the belief that it's necessary sometimes arises. You can actually buy Grignard reagents directly from chemical suppliers, skipping the time-consuming and notoriously unreliable preparation step. The drawback of buying Grignard reagents though is that they are air-sensitive. So you need air-free techniques and occasionally a glove box to use them effectively before they go bad. If you're in a high-throughput lab that uses Grignard reagents every week, then this can be dealt with. For most chemists though, and almost all amateurs, making the Grignard reagents on the spot like we are here is the more flexible option, and we can accept the time loss and reliability issues. Anyway, we have now added all of the bromohexane mixture. I'm going to let stir for another half hour to ensure complete reaction. Since bromohexane is hard enough to make, I used an excess of magnesium metal to ensure it was all used. For some chemists though, having bits of magnesium in the reaction hurts their later steps, so they instead use excess alkyl halide. You'll have to decide for yourself which reagent you use more of. Anyway, we now add our desired carbonyl compound. For this particular run, my target compound is 2-methyl-2-octanol. So my carbonyl compound will be 40 grams of acetone dissolved in 100 milliliters of diethyl ether. Once again, we add slowly using the pressure equalized dripping funnel, being careful not to let it heat up too much. The acetone reacts with the hexyl magnesium bromide to give us 2-methyl-2-octane oxy magnesium bromide. This is the actual Grignard reaction. Essentially, we're adding a hexyl group to the carbonyl carbon of the acetone, forming a carbon-carbon bond between them. It's an extremely versatile reaction. Once you get over the hard part of actually obtaining the Grignard reagent, the reaction itself is very robust and high yielding. Anyway, as we progress, the products will start to precipitate out. Keep vigorously stirring so they remain suspended and don't solidify. Once all the acetone is added, continue letting it react for 10 minutes. Now having an alkoxide salt is usually not all that useful, so we'll need to perform an aqueous workup to obtain the alcohol, and we'll need to run some distillations to purify it. First, we get 400 milliliters of water. Now we place it in an ice bath and let it cool for half an hour. With vigorous stirring, we slowly add our reaction mixture from earlier. Considerable heat is generated as the alkoxide reacts to form 2-methyl-2-octanol and a dense precipitate of magnesium hydroxybromide. Overheating is really easy if you go too fast. Eventually, all the reaction mixture is added and we now have a new mixture of gelatinous magnesium hydroxybromide, ether, and our target alcohol. Unfortunately, they're not going to separate cleanly, so we'll need to dissolve the precipitate first. To do this, we slowly titrate in a 30% solution of hydrochloric acid until the mixture goes clear. You can use any concentration of hydrochloric acid. We're essentially dissolving the magnesium hydroxybromide into magnesium chloride and bromide salts. I didn't use the acid at the beginning because I found the heating was so great that the ether instantly boiled off and splashed out my product. It was similarly unworkable to directly add acid to the raw reaction mixture. So doing it in 2 steps, mixing it with water first and then adding acid, was more controllable. Anyway, once the mixture goes clear, turn off stirring and let the organic and aqueous layers separate. On top should be the ether layer containing our target 2-methyl-2-octanol, and on the bottom should be water and magnesium chloride and bromide salts. Using a separatory funnel, we separate the layers and collect just the upper ether layer. Now the easiest way to remove the diethyl ether is to set up a simple distillation apparatus and distill it off. You can save your ether for reuse, although it should be stored over sodium to destroy any contaminants. Once the temperature rises past 40 degrees Celsius, most of the ether has been removed and now it's a matter of separating out our target alcohol. Let the mixture cool and reconfigure around it a fractional distillation setup. Slowly distill off the components up to 9 degrees Celsius. This is mostly leftover ether, some acetone, water, and a bit of our target alcohol. Once it hits 90 Celsius, stop heating and let it cool. Now on top of the fractional distillation column, we install a Dean-Stark apparatus. Turn on the heating and start removing the water. The reason why I'm doing this is because there is a lot of water remaining in the mixture. Sure, we removed most of it by separation, but ether dissolves a small amount of water in itself. When we boiled off the ether, a lot of that water is left behind. Now water forms an azeotrope with a lot of organic substances, including our target alcohol, so we can take advantage of that to remove the water using azeotropic distillation with our Dean-Stark apparatus. For further information about using the Dean-Stark apparatus, you can check the video description. Now I simply didn't distill off the water since I didn't want the azeotrope to carry off too much of our valuable alcohol. Anyway, as usual, keep running the trap and emptying occasionally until no more water comes out. Then add all the organics back in and reassemble the condenser onto the fractional distillation column. Now we distill off all the higher boiling components. Hexanol will be a major contaminant, so discard everything below 177 degrees Celsius. Above this temperature, we are collecting our target 2-methyl-2-octanol. And that is our target 2-methyl-2-octanol. Now I want a variety of tertiary alcohols for my upcoming experiments in making alkali metals, so now I'm going to try and make 2-methyl-2-butanol, also known as tertiary amyl alcohol or T-amyl alcohol. So this time I'm going to start with 20 grams of magnesium turnings and add in 150 milliliters of diethyl ether. Now we assemble on top a condenser column, and on top of that we suspend our dripping funnel containing 80 grams of bromoethane and 125 grams of diethyl ether. This approach accomplishes the same thing of allowing us to add our reagents as my previous approach of using a Claisen adapter to mount the condenser column and funnel side by side. Looking back, I think the Claisen adapter is more convenient since it works with a short fume hood. Mounting them on top like this requires you have a very tall fume hood, and you have to reach up higher, which is inconvenient. It's hard to see in this video, but there is a gap between the condenser column and the dripping funnel so the vapors can rush out, and we don't get overpressure in our dripping funnel. Anyway, the rest of the reaction proceeds very similarly to our previous one. We start up our reaction by adding a couple of grams of bromoethane and letting it sit for 10 minutes before we stir it up. This time it reacts right away. The boiling shows an exothermic reaction occurred, so the magnesium is activated, and we can then drip in our bromoethane and ether solution. This time we make ethyl magnesium bromide, which is much shorter than hexyl magnesium bromide. Now once that's all added, we now add in a mixture of 50 grams of acetone in 100 milliliters of diethyl ether. It is here where our ethyl magnesium bromide reacts to produce our target T-amyl oxide magnesium bromide. When the reaction ends, it'll cool and some of the compounds will precipitate. Now once again we add our reaction mixture to cold water, but this time I'm going to add it directly to ice water rather than simply cooling the water with ice as before. This is a bit faster, but is somewhat more cumbersome because it's very difficult to stir ice like this. Once again, we're hydrolyzing our alkoxide to make the alcohol and precipitate magnesium hydroxybromide. We then titrate with hydrochloric acid until it clears. And there is our layer of ether containing our target tertiary amyl alcohol. Now we just use a separatory funnel and separate out the upper ether layer. We then perform a simple distillation and remove all the lower boiling components up to about 80 degrees Celsius. Now, like the 2-methyl-2-octanol, we have a lot of water left over that we need to remove. Assemble the distillation apparatus into a Dean-Stark apparatus and proceed to remove all the water. Once it's all out, we then assemble the apparatus into a fractional distillation apparatus again and proceed to fractionate our components. Discard everything below 95 Celsius and then start collecting. For greater purity, you can discard everything below 100 Celsius. Anyway, T-amyl alcohol boils at about 102 Celsius, so we are now collecting our tertiary amyl alcohol. And there is our T-amyl alcohol product, a low purity forerun and a higher purity end run. But these will be suitable for my experiments. Now, so far we've been adding Grignard reagents to ketones, specifically acetone. Acetone is essentially two methyl groups attached to a carbonyl group, so this makes any alcohol we produce from it also have two methyl groups. I want a much larger alcohol for my future experiments. Methyl ethyl ketone, also known as 2-butanone, is one option, but it only increases one of the groups by one carbon. So instead of a ketone, I'm going to use an ester. What happens in this case is that one equivalent of the Grignard reagent first reacts with the ester and causes the ester alcohol to leave and produces a ketone. Then another equivalent of Grignard reagent can be added to produce a tertiary alcohol built up from two Grignard reagents and the carboxylic acid that was part of the ester. So let's try that. Since we've already done two Grignard reagents, I'm going to gloss through the details. But briefly, I started with 20 grams of magnesium metal turnings and added 150 milliliters of purified diethyl ether. Once again, I started up with a shot of bromoethane and add a total of 80 grams of bromoethane along with 125 milliliters of diethyl ether. After making our Grignard reagent, I then performed the actual Grignard reaction and this time dripped in 40 grams of ethyl propionate. I still had a lot left over from my previous videos on making pure methamine. As stated earlier, ethyl propionate is an ester and reacts with one equivalent of ethyl magnesium bromide to make 3-pentanone. This quickly reacts with another equivalent of ethyl magnesium bromide to make 3-ethyl 3-pentoxy magnesium bromide. You might be wondering if you could isolate the 3-pentanone itself. This is extremely difficult even if you use exactly one equivalent of Grignard reagent, because the resulting ketone would compete with the remaining ester to react with the Grignard reagent. You get a mixture of products. This doesn't mean you can't selectively make ketones with Grignard reactions, you just need to use different substrates like nitriles. Anyway, after the reaction is finished, we once again add ice water to hydrolyze it. I'm using a lot more this time so I can add in faster. Once it's all hydrolyzed, we titrate in hydrochloric acid. I've been using hydrochloric acid because it's cheap. You can also use sulfuric acid, acetic acid, or even sodium bisulfate. Hydrochloric acid is actually not the best acid to use because there is some danger of chlorinating the tertiary alcohol by substitution at high concentration. If you carefully titrate this, then this problem should be negligible. But using an acid like sulfuric acid would reduce the risk considerably. Anyway, we now separate the two layers using a separatory funnel and recover the ethyl layer on top. Once again, we set up for a simple distillation. Distill off the ether and all the other components up to 85 degrees Celsius. Set up the Dean-Stark apparatus and again remove the residual water. As you can see, a Dean-Stark apparatus is very useful in organic chemistry. Removing water is such a common practice that having special equipment for it saves a considerable amount of work. I haven't been using molecular sieves because I don't need ultra-dry reagents. Wasting sieves isn't worth it when a Dean-Stark apparatus removes the bulk water I desire for just the cost of electricity and time to run it. Anyway, once the drying is done, we set up a fractional distillation column and start recovering our tertiary alcohol. 3-ethyl 3-pentanol has a boiling point of about 140 to 142 Celsius, so discard everything up to 140 and start collecting our tertiary alcohol. And there it is, 3-ethyl 3-pentanol. Now I want an even bigger alcohol than this. So the next logical step would be to use our bromohexane and add hexyl chains, but that still leaves a tiny little ethyl chain. We could use a longer ester like ethyl heptanoate, but that's not easy for me to get. We can instead use an organic carbonate. Organic carbonates react with Grignards to first produce esters. Then they react again to produce ketones, and finally they produce alcohols. The interesting thing about this is that it doesn't matter what the original substituents on the carbonate were. They're always lost. Only the Grignard reagent matters. So we can use any organic carbonate we want. So I'm going to do that. This time I'm starting with 15 grams of magnesium metal and 150 milliliters of ether. Once again we start our reaction with a shot of bromohexane and I'm dripping in 75 grams of bromohexane in 50 milliliters of diethyl ether. Now the organic carbonate I'm going to drip in is 15 grams of propylene carbonate dissolved in 50 milliliters of diethyl ether. As described before, we're essentially making 7-hexyl-7-tridecanol, a very large tertiary alcohol. Interestingly, I got a precipitate much sooner. Anyway, once again we add the solution to an equal mass of ice-cooled water and hydrolyze it. Then we titrate in hydrochloric acid until it clears. We use a separatory funnel to recover the upper ether layer that contains our target alcohol. It might be helpful to wash the ether again a few times with water to remove the propylene glycol since it's water soluble. Eventually, we distill off the diethyl ether again using simple distillation. Now I did try and use the Dean-Stark apparatus to remove water, but then I found there was no point. The boiling point of 7-hexyl-7-tridecanol is far too high at above 300 Celsius, so it would form a negligible azeotrope with water. In fact, the Dean-Stark apparatus stopped working once the lower boiling components filled the trap and the residue could no longer reflux since the boiling point was too high. So I reassembled the distillation apparatus and simply cranked the heat to maximum and boiled off all the lower boiling components including water. My hot plate is not hot enough to distill 7-hexyl-7-tridecanol, so I wasn't worried about losing it. Once it stopped distilling, I let it cool. And here is our residue containing our target alcohol. It's full of impurities and I want to purify it. But having a boiling point beyond the limit of my hot plate, distilling it directly is not an option. Fortunately, we can use steam distillation. I add in distilled water, about 150 milliliters, and built around the flask the heavy return Dean-Stark apparatus. You can check in the video description for more details on it. Basically, rather than return the lighter components for reboiling, it returns the heavier components. In this case, water. The target alcohol is lighter than water, so it floats on top and stays in the trap. The beauty of this approach is that even though our target compound has an excessively high boiling point, as long as it forms an azeotrope with water, even a negligible one of just a few percent, it can be distilled over and purified. This technique is used extensively for recovering essential oils that would otherwise burn if heated too high. Unfortunately, being a negligible azeotrope means this steam distillation is extremely slow. Only tiny amounts of our target alcohol come over with every drop. I had to run this for a full week to get useful recovery. Also, I had numerous problems with foaming that I never quite solved, so I had to reset often and wasted even more time. Eventually though, I was able to recover just the alcohol. The vial on the left is a pure sample, while the one on the right is discolored because I left the distillation running for too long, and some of the impurities started to distill and foam over. After wasting a couple of months on this, I decided not to redo it. Anyway, we now have a nice collection of various tertiary alcohols. Here are the respective weights and yields that I obtained. They're all pretty bad because I'm working under amateur conditions. But in general, Grignard reactions are pretty high yielding if you work with pure lab-grade chemicals and large scales. So what am I going to do with these alcohols? I want to try and make various alkali metals like potassium and maybe even sodium. Now I know I already discovered how to make sodium by amateur means, but a method to make it without setting things on fire would be even better. Thanks for watching. Special thank you to all of my supporters on Patreon for making these science videos possible with their donations and their direction. If you're not currently a patron but would like to support the continued production of science videos like this one, then check out my Patreon page here or in the video description. I really appreciate any and all support.